Pop quiz. Which corner does the proton end up in? Left or right? Use the pKa numbers and lock in your pick. Time's up. The answer is the products. Here's why. The acid on the product side has a pKa of 10, which makes it weaker than the acid on the reactant side with a pKa of 5. That makes ΔpKa plus 5, so the equilibrium constant KEQ is about 10 to the 5th toward products. There's a clear pattern here, and in a moment, we'll explore the general rule. In this video, you'll learn a fast and reliable way to predict which side an acid-base equilibrium favors using pKa. You'll see how to identify the two acids, compare their pKa values, calculate ΔpKa, estimate equilibrium constant, or KEQ, and avoid common traps along the way. In Bronsted-Lowry terms, acids donate H+ and bases accept it. In any proton transfer equilibrium, the favored side is the one with the weaker acid and the weaker base. pKa lets us spot that quickly. Here's the rule of thumb. ΔpKa equals the pKa of the conjugate acid on the product side, or Hb minus the pKa of the acid on the reactant side, or HA. If ΔpKa is greater than 0, products are favored. If it's less than 0, reactants are favored. And as a rough estimate, the equilibrium constant is about 10 raised to the ΔpKa. For example, compare hydrochloric acid, HCl, and hydronium, H3O+. Since hydronium has a higher pKa, meaning it's the weaker acid, the equilibrium shifts toward the products. ΔpKa is negative 1.7 minus negative 7, which is about positive 5.3, giving a KEQ of roughly 10 to the 5th. From this, notice the bigger principle. A higher pKa means a weaker acid, and that side is favored. So far, we've nailed the core steps. Identify the two acids, compare their pKa values, calculate ΔpKa, and predict which side is favored. Want to turn those milestones into mastery? Tap the link to access the practice test, flashcards, and study guide, then jump right back into the video. Lock in what you learned and keep going. Now, let's take acetate formation. Acetic acid is more acidic than water because its conjugate base, the acetate ion, is resonance stabilized. When we compare acetic acid with water, the acid on the product side, ΔpKa, comes out to about positive 10.94. That means the products dominate by around 10 to the 11th. In water, this reaction goes essentially to completion. Next, let's look at terminal alkynes. Their CH bond has a relatively high pKa, so they're only weakly acidic compared to most familiar acids. But if we use amide, NH2-, the conjugate acid that forms is ammonia, NH3 with a pKa of 38. That makes ΔpKa about 13, so the equilibrium constant around 10 to the 13th. The acetylide ion forms strongly, but not every base wins. Take phenol and bicarbonate. ΔpKa is 6.3 minus 10, or negative 3.7. That's less than 0, so the equilibrium favors the reactants. A good reminder that stronger isn't always better. Before we wrap up, there's one more important nuance. pKa values depend on the solvent. In water, very strong acids are leveled to hydronium and very strong bases to hydroxide. So always choose the right pKa table for your solvent or your predictions may drift. So let's formalize the move set. Step 1. Identify the acid on each side. Step 2. Look up the pKa values in the correct solvent table. Step 3. Compute ΔpKa. Step 4. Favor the side with the weaker acid and base. And step 5. Estimate the equilibrium constant if you want the scale. It's simple, fast, and powerful. To recap, when ΔpKa is greater than 0, the equilibrium leans toward the products. When it's less than 0, it leans back to the reactants. And the size of that shift? About 10 raised to the delta pKa. That one number gives you the scale of the whole equilibrium. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.